and share screen. Okay, cool. So we're back. All right, so last time we did this proof. I just want to start by saying what we did last time, that if phi witnesses the true property, then T has TP1 or TP2, where really what we proved is that either phi has TP2 or some conjunction of instances of phi has TP1. And okay, this proof, to write it properly is a bit grungy, I know, but let's just, without even writing anything, let's just try to reconstruct the architecture of the argument so that people can hold it in their head. So step one, you assume that you have a witness to the tree property that is not a witness to TP2. And you know that you can make that witness to the tree property S indiscernible. But if you have a witness to the tree property which is S indiscernible, but it's not a witness to the tree property of the second kind, then you can make it STR indiscernible, which is like an upgrade. This is the one where you don't have predicates naming the levels anymore. You just have this preorder that identifies when things are longer or not. Okay, then you start looking at 0 concatenated with 1, 0, 0 concatenated with 1, 0, 0, 0 concatenated with 1, and so on and so forth. And you know that that becomes inconsistent at some stage. Because if it's consistent, then you can look at this array of incomparable things extending some number of zeros. And if that's consistent, then any function snaking through that array will be consistent, but the rows are inconsistent by the assumption that you started with a witness to the tree property. And that would give you TP2, which you have assumed you don't have. So eventually these things become inconsistent. So then working over some initial segment of these things, you end up finding some configuration where if you go a little bit to the right and a lot bit to the left, they're inconsistent. And then you just switch directions and you do the same thing, where now you look at 1 concatenated with 0, 1, 1 concatenated with 0, 1, 1, 1 concatenated with 0. These things have to be inconsistent for the same reason. And you find a situation where if you go a little bit to the left and then a lot bit to the right, you're inconsistent. But also because you're sort of adding this to what you did before, if you go a little bit to the right and a lot bit to the left, you get something inconsistent. And then there was a small trick at the end to make sure that even at the same level, you're inconsistent. And what does that give you? That gives you a tree where paths are consistent and incomparables are inconsistent. That is the tree property of the first kind, which is exactly what we wanted. So okay, it's kind of fussy to get it written precisely, but at the same time, okay, the basic idea is you make things as indiscernible as you can. You take conjunctions so that you can reduce your inconsistency to pairwise inconsistency. And if you play games long enough, then eventually you get it. Are there any questions about the way that argument went?
Yeah, I have a quick question. At the very beginning, we had to bump up the S indiscernibility to STR indiscernibility. And I guess that
Right.
followed from the lemma that looked like the delta system kind of thing. How did that work? How did that implication work?
Oh, yeah, sure. So hold on, I think my sharing screwed up. Let me fix that. Okay, while this is loading, let me just say, oh no, it's, okay, now we're back. It's being weird. Okay, so I bet I can find the statement actually. So here's this lemma, right? Like if you have an NTP2 S indiscernible witness to KTP, then you can find something where this gives you this inconsistency, right? So what is the idea? Okay, now I need some free space. Okay, so in the original tree that I was looking at, this S indiscernible tree I was looking at, if I take a node and I look at some things that are at the same level, let's suppose n is 2 here. So I know that if I take two things that are at the same level and they're incomparable, then they're, well, two is too small maybe, but no, it's fine. So two things that are at the same level and they're incomparable, then they're inconsistent. Suppose I have this situation, right? Now, if I move to something STR indiscernible, let's suppose this is like level 0 and this is level 1. is it possible, we ask, is it possible for these two things to be consistent? Okay, if these things are consistent, then what does that mean? Well, this comes from something locally based on the situation we started with, right? So that means that if this, let's call this node eta and this node nu, then I can find some, so I have nu and eta. I can find some nu prime eta prime, which have the same quantifier free type, such that, okay, let's say these are the b's, and the original thing I started with was a's. Well, I find two things that have the same quantifier free type, such that like a nu prime, a eta prime are consistent, like these instances of phi. Okay, now if these two things have the same quantifier free type, now in the language of LSTR, what do I know? Well, I know that they're at the same level, and that's it. I don't necessarily know in this case. I mean, even though the tree I took them from, they were successors of a common node, that might not be true in the tree that they come from. I mean, in the A's. Does this sort of make sense? Like, if the problem is, if I start with k things that are forming this like kind of delta system in the STR indiscernible tree that they're based on, I know that any formula that's true of the things that they index has to be true of something in the original tree indexed by something with the same quantifier free type. Now, if I'm interested in the same quantifier free LS type, then the quantifier free type will tell me these k nodes are children of a common node, because the quantifier free type will tell me they're at level n plus 1 and that their meet is at level n for some n. But in the STR language, all I know is that they're at the same level and they properly extend their meet. But I don't know the distance, because all the language tells me is that it's bigger. So it could be that they extend the meet by 2. It could be that one of them is like the meet concatenated with 2 zeros. The other one is the meet concatenated with 1, 1. The next is the meet concatenated with 2, 2 or something, right? So because the tree property by itself doesn't tell me that things that aren't descendants of a common node will be inconsistent, we needed the lemma to know that if we took something locally based on our witness to the tree property, that it would still be a witness to the tree property. Does that answer the question? I mean, this is really subtle. I mean, so some of the people that are watching this were texting me afterwards saying like, okay, explain this step. And the point is just that you start with something S indiscernible. If you take something STR indiscernible on it, in general, that need not be a witness to the tree property. So let me just draw a picture. I mean, one more picture, which I think is important. So suppose you have a witness to the tree property with the property that anytime I take two things which are incomparable, but not children of a common node, they're consistent. So it could be, for example, that like these things are consistent. The tree property will tell me that these things are k inconsistent, these things are k inconsistent, these things are k inconsistent, but the two things in green could be consistent with one another. Then notice that inside this tree, these two green things have the same quantifier free type as these two black things. So these two green things, which are consistent, have the same quantifier free type as two children of a common node in the thing that they're locally based on, in the LSTR language. And so that means that if I pass from my witness to the tree property to an LSTR tree locally based on it, I don't know that children of a common node form a k inconsistent formulas unless I knew that that were for any k nodes that formed this kind of delta system situation.
Okay, so I think I get it now. So in that lemma about the delta system kind of looking thing, there was no bound on sort of the heights of these, but there was a constraint about them being like k inconsistent. So
Yeah,
it's like a
yeah,
width.
yeah. So where did the bound come from? I mean, maybe this is worth saying. So if I'm in TP2, then there's a maximal n such that I can find a mutually indiscernible array of height n such that rows are k inconsistent and paths are all consistent. You know, like if I could do that for arbitrarily large n, then by compactness I could build one of countable height, and then I would find TP2. So compactness gives me this n. And then we can just remember how the proof goes. So we suppose that children of a common node are k inconsistent. And then we said, okay, let's suppose that I'm looking higher up. So I'm supposing now that something like this point and this point is consistent. And this point. Let's suppose our n is 3, right? Then we say, well, we can look at this row, and this row, and view this as a height 3 indiscernible array. If these purple dots are consistent, then by S indiscernibility, this forms a mutually indiscernible array in which the rows are k inconsistent because it comes from a witness to KTP. So children of a common node are k inconsistent. So these rows are k inconsistent. But if the purple things are all consistent with one another, then that means that any way of snaking through these 3 rows will give me something consistent. And that violates the choice of n. So this is where that n comes from. It comes from this compactness argument that tells you have a bound on how close to an approximation to in TP2, or to TP2, sorry, that you find.
Yeah, okay. I think the thing I was confused about is the height of the array is sort of the width in the other picture. So
Right, yeah.
I was
So the
thinking there'd be.
challenge here is to somehow look at the tree correctly and find where the indiscernible arrays are. And as we've seen, there are actually quite a few mutually indiscernible arrays living inside this tree, right? So in this argument, you see that like the height of the array really is like the width of this tree. But then also in the argument for Shallah's second dichotomy theorem, we had a different mutually indiscernible array, which is coming from this collection of incomparable things sort of shooting off the all zeros branch or the all ones branch. And so this is why this is part of the reason why tree indiscernibles are such an interesting tool, because if you have an indiscernible tree, then that contains just multitudes of different indiscernible arrays sitting inside, and those all have something to say to you. Yeah. So I'm glad we revisited this because it's a really complicated proof. And like you said, I mean, like this proof was written down for the first time sometime in the early 80s, but I think it was maybe like the last 5 years that someone actually carefully wrote down the correct argument, despite this being something that people cared about and thought about for a lot of time, because like just to give all the details is kind of grungy. So I don't know, I think this is maybe the first time that someone has given a lecture course in which this theorem was proved. And so it's good to review and make sure that it's done carefully. Okay, so now we're going to move on to forking, which is good because I think like I love these arguments. I love all this stuff involving tree indiscernibles and stuff, but it's a bit, I don't know. It's the kind of math that has so many confusing details that a lot of it is something that I think you can sort of best do on your own once you've seen the right pictures. But it's not so conceptual, maybe hard to discuss. The stuff we're going to do next is more conceptual. So hopefully that makes everyone happy. So what's the idea? We're going to talk about forking. All right, so the plan is today we're just going to talk about forking in general, what properties we can expect it to always have. Then in the future lectures, we'll sort of restrict our attention to the case where T is simple and see what we can say, and then we'll go from there. But forking makes sense in any theory, and this was introduced by Shallah. So let's give the definition. So the first thing we're going to define is dividing. So phi x a. So a will be a set of parameters. Phi x a divides over a if there is an a indiscernible sequence ai, I less than omega, such that if I move my formula along this indiscernible sequence, I get something which is inconsistent. Okay, so dividing, you should think of dividing as telling you that this set is small. And why? Well, the idea is if phi defines a set somehow huge, some measure one kind of thing, then as you move it around inside your model, you expect to see lots of overlap. I mean, just imagine, like you take a measure one set of the interval of the interval 0, 1. You look at many translates according to some action, and then you expect that these things should have big overlap because it's measure one. So if something's measure 0, if it's the complement of something big, then you expect to be able to move it around a lot and have small overlap. So what this is saying is a set divides if I can move it along some indiscernible sequence in such a way that the instances are almost disjoint. They're maybe not pairwise disjoint, but the fact that this is an indiscernible sequence and it's inconsistent means that by compactness there's some k such that any k of them are inconsistent. So that says it's pretty small. Now, small sets typically form ideals. So the forking formulas are the formulas that are in the ideal generated by the dividing formulas in the Boolean algebra of formulas up to equivalence. More precisely, you say phi x a forks over a. And I'll just write this line instead of writing over because it's a bit simpler. If phi x a implies some disjunction of formulas where each ci divides over a. So what does this say? This says that phi is contained in a finite union of dividing sets. I mean, if you look at the set defined by phi, that's contained in a finite union of sets defined by formulas that divide. So if you think about dividing as like measure 0, then it's saying that it's in a finite union of measure 0 sets. That should be measure 0. So this is like it's literally the same as the ideal generated by the dividing sets. Okay, and then this is for formulas, but it extends naturally to types. So you say a type P or divides over A if P implies a formula that forks or divides over A. And this gives you a notion of independence. So you write A ind superscript D, B over A, if and only if the type of A over AB does not divide over A. So maybe I should label these things. So forks. I'm defining this thing. And you do something similar with forking. Okay, so I told you one interpretation of this notion already. Dividing is like saying that you can move around a lot and get a family of sets that are almost disjoint, and that means that it's small. Now, the way that you think about this independence relation is what this is saying is that A is independent with B over capital A. If using B as a parameter, I can't learn any new interesting information about little a. What do I mean? I mean, I can't use the parameter b to trap a into a small set. Of course, using b, I can say more than I could just using the parameters in a. For example, I can say that a is not equal to b, but almost everything's not equal to b. That's not particularly interesting information. The thing that I can't say is like a equals b, because if I said a equals b, then I'm learning lots of new information about a that maybe capital A didn't know. So you can also think about it this way. I mean, this relation, in principle, it's not symmetric, right? It just says using b, I can't learn about a. But we'll see in interesting cases it turns out to be symmetric. Not all, but in some interesting cases. Okay, so let's
Nick?
think about an example.
Yeah, Nick?
Yeah.
Just a quick question. The definition of dividing and I guess also forking, we have this parameter a in the formula. What is the significance of including that parameter with the definition?
Oh, thank you. So you have this industry sequence with a0 equals a. Thank you. Oh my goodness. Yeah, that matters. So you're moving. Okay, so this is why you think about it as moving the formula. So I have some indiscernible sequence that starts with the parameter. So what I'm doing when I'm moving is I'm moving my parameter from one thing with the same type to something else with the same type to something else with the same type along this indiscernible sequence and obtaining a k-inconsistent collection of formulas. So the significance there is very important. It says that like this is where your indiscernible sequence starts. So you like the question of whether things divide has a lot to do with the type of that parameter, because of course some things will divide and some things won't, and that's almost always going to depend on the type of that parameter. So thank you. Yeah, that was just a mistake in writing. I should have said a0 equals a. Thank you. Yeah, and this should get labeled forks. Okay, so I'm going to give some examples where forking and dividing are different, but I will say that in almost every case that we care about, for us, forking and dividing will be the same, although that's almost always a theorem. I mean, it's like kind of hard to see. So when we move on to, for simple theories, it's not so hard. We will prove that probably in 2 lectures. For NTP2 theories, it'll take us a whole week, and it's like a hard theorem, a famous result of Chernikov and Kaplan. I mean, famous for model theorists. It's like it was a big deal in model theory. And then, you know, in other contexts, it'll be work. Okay, but we'll see that they're easy to understand examples where they come apart. All right, so let's think about the simplest example. So for me, this is, okay, let's do the simplest possible example, and then we'll do one extremely simple example, which is slightly more complicated. So let's do L is empty, the empty language, and T is the theory of an infinite set. Okay, so which formulas divide? Someone can tell me the answer to this question. How about the equalities? That turns out to be the only thing you can say, right? So if anything divides, it's got to be that. So if you have A is some set, and B is not in A, then X equals B divides. Think about why. So I've got a model of my theory. I've got some set A, and I've got some B. What do I do? Well, I just take any collection of pairwise distinct elements. So I think of B as B0, B1, B2, B3, B4. These are all distinct. It's easy to see by quantifier elimination that in fact this is an indiscernible sequence already, just saying that they're different. And now I look at my formula as I move it along this sequence. And what do I note? I note that X equals BI, I in omega is 2 inconsistent. Any 2 of those are distinct, I mean, incompatible, because I can't be equal to 2 different things. Okay, so this is dividing. Now let's think about, is this clear? So let's think as in particular about like what is independence. So if I hand you two sets, A and B, when does this take place? When is A independent with B over C? Does anyone have a guess? For those of you that haven't studied this notion before? So how about the following? If I'm given this happens if and only if A intersect B is contained inside of C. And this conforms to our intuition, right? That what this says is that you can't use the new parameters in B to learn new things about A that C didn't already know. So like if you have an equality between B and A, then if it comes from C, then C already knew it. But if it comes from B, then it didn't. So let's just think about why. So you have your set C living inside some model, and you've got A and B. And let's suppose you have C here, and this orange blob will be what we call A, and this red blob will be what we call B. So this is A, and this is B. So we saw already that if A and B are the same, then we have dividing. Because if A and B are the same, then the type of A over B contains the formula x equals B. B is not in C. So I can take a collection of pairwise distinct elements, and the collection of formulas that say x is equal to B0, x is equal to B1, x is equal to B2, these are all incompatible, so I get dividing. However, just note that the formula x equals C is also in the type of A over BC. Does that divide? Well, no, because the base here is C. So if I want to divide over C, I have to move my formula along what kind of sequence? A sequence that is indiscernible over C. So all of the elements of that sequence have to have the same type over C, but C is an element of C. So the type of C says I'm equal to this element. So any indiscernible sequence in that element has to be trivial. And if that's true, then it can't be inconsistent. Of course, like anytime I take an indiscernible sequence starting with C over C, it's going to say C0 equals C, C1 equals C, C2 equals C, and all those things are compatible. Okay, so that's a description of forking in this case.
Sorry, Nick.
Now let's do.
I have a question.
Yes.
So you wrote an independence relation between sets A and B, though in your definition you only had independence like between elements.
Yeah, so between tuples. So if I write a set, then I mean anytime you take a tuple enumerating it. So okay, this is like the standard model-theoretic thing. You can either talk about independence for sets, and what that means is whenever you fix an enumeration, there's nothing in the type, with those variables such that these things are true. I mean, so for sets or tuples, it's the same. Although to talk about the type of a set doesn't really make sense. You have to sort of enumerate it to associate each element with a variable. But once you do that, then it makes sense.
So the A and the capital A's and capital B's are infinite sets. So you're talking about infinite tuples, and
they can be anything. Okay. I mean, of course, formulas are finite, and we've only really said what it means for a formula to fork or divide, and then we said what it means for a type to fork or divide is that it implies a forking or dividing formula. So of course, if two infinite tuples divide with one another, then there has to be some formula in the type of one infinite tuple which divides. That's only going to use finitely many variables. So it reduces to a question about the finite subtuples. But in principle, there's no problem talking about infinite objects on the left and the right.
Okay, thanks.
Yeah, no problem. Okay. So let's think about another very simple example, and then we should probably try to prove something. So here's an example which I think we've talked about before. So the language has a single binary relation. And the theory just says that I'm in an equivalence relation with infinitely many infinite classes. So let's take two elements, A and B, and then we'll take a third element, C, all in the same class. Okay. So my first point is that A is not dividing independent with B over the empty set. Why? Well, the type of A over B implies that A is equivalent to B. It implies the formula EXB. Now, inside this picture, I can take an indiscernible sequence like this, where I take an element 1 from each class. You can check by quantifier elimination in this structure that if I just take any collection of pairwise inequivalent elements, that will be indiscernible over the empty set. And now, if I look at the collection of formulas, E, X, Bi, I less than omega, this is 2 inconsistent. So this is going to be B0, this is B1, this is B2, and so on. Okay, does that make sense? I can't be simultaneously equivalent to B0 and B1 because they're not, themselves not equivalent, and equivalent solutions are transitive. Okay. But now let's think, okay, are A and B independent over C? So the question now is, are A and B dividing independent over C? And the answer here is that they are. They are. Because although the type of A over B says A is equivalent to B, it says X is equivalent to B, if I move B along an indiscernible sequence in a type over C, I look at a C indiscernible sequence in the type of B, all those things have to be equivalent because part of the type of B over C says I'm in the class of C. So if I took an indiscernible sequence starting with B over C, it would look like this. And what does the type of A over B say? It says I'm in the same class as B and I am distinct from B. So all I have to do is find some element which is in the same class as B and not equal to any of these elements. And that I can do by compactness because the class is infinite. Does that make sense? So does anyone want to venture a guess for what independence is in this case? What dividing independence looks like? So I have three sets. Oh, oops. A, B, and I want to know when they're independent over C. And this is going to happen when two things happen. So one of them is, of course, that A intersect B is contained inside of C. This is always a requirement. But also that if I look at so plus, let me write this here. If I look at the classes of elements of A, and I take the intersection of that with the classes of B, that the intersection is contained in the classes of C and C. So of course, the empty set doesn't have any classes in it. And so what we saw is that when I represented a class, when I looked at A and I represented some class that was also represented by something in B, because that wasn't represented by anything in the base, I had dividing. So this is a characterization of dividing in this case. Notice here it's symmetric also. And you can check that it's equal to forking. Okay, is that clear? Are we starting to see how this makes sense? So this is a good example to think about. This is like the simplest non-trivial example of a structure where notions like independence have some meaning. It's not just equalities. All right, so now let me give an example where forking does not equal dividing. So what we'll do is we will take S1, so this is the circle, together with the relation C. So this C is ternary, and C holds of X, Y, and Z if X and Z are not antipodal, and Y is on the, I think it's called a minor arc between X and Z. So suppose that I have my circle and I take 2 points that are not, that don't, such that the line segment connecting them is not a diameter. Then that splits the circle into 2 pieces, one of which is smaller than the other. This is the point of making sure that they're not a diameter. And what I'm saying is that Y, sorry, I wrote Y here, but I meant Z. X and Z are not antipodal, so their line segment connecting them is not a diameter. And then I look at the minor arc between them, and I want Y to live somewhere there. Okay, so take the real circle and expand it with a relation like this, and then look at the theory of that structure. It's interpretable in the real closed field, I guess. Yeah, I mean, you think about the plane of real numbers, and you look at the solution set to x squared plus y squared equals 1, and then this relation is certainly definable. Okay, now what you notice is that x equals x, like nothing, the formula that says nothing at all, will prove the following. So let's fix 3 points. So let me give these a color. So we'll fix 3 points. Let's call this A. Oh no, I don't want that. I want A, B, and C. So I pick 3 points, and let's just choose them such that there are 120 degrees between any two. So then this is going to prove that x is going to be between A, or x is going to be between B and C, or x is going to be between C and A. Right? I mean, every point on the circle is going to be between 2 of these. Oh, and when I say between here, let's say it's inclusive, just so that it really is true that all of them. So you can either be equal to x or y, or you can be between them. So in some inclusive way. Okay, does everyone buy that? Every point on that circle is in one of these 3 intervals. And also C, AB divides. Why? Well, you can check that if I look at the circle, so this A and this B will have the same type as this. Let's call it A0, B0. Maybe I should label them like with color. So like we'll say this one's red and this one's blue. And then I can look at A1, B1. So this is like red and this is blue. And then another one, A2, B2, which is red and then blue. You can form an indiscernible sequence like this. And if you do that, then you'll see that C, AI, X, PI, I less than omega, is too inconsistent. This circle doesn't come equipped with any notion of distance. So of course I can replace the 120 degrees that I started with something really small. So I could break it in two. You know, I could start with something 120 degrees and then have another thing which is disjoint from it of 60 degrees and then something of 30 degrees and so on and so forth. So I can get smaller and smaller and smaller intervals, all of which are disjoint, and I can't be in any two. So this formula divides. But x equals x, of course, doesn't divide. It doesn't even have any parameters. I can't move it. So likewise, for other two formulas, but x equals x does not divide. So x equals x forks, but does not divide. Okay, so this is a nice example. Another example I know is you could look at this like two-sorted structure where you have all subsets of the natural numbers and the natural numbers, and you have the element relation between the two sorts. So you have the natural numbers and the element relation in the subsets. And every set is going to be contained in the union of the evens or the odds. So you have x equals x will prove x is an element of the evens or x is an element of the odds. But you can check using just an automorphism of this whole structure that any two infinite co-infinite sets have the same type. So saying that x is in the evens, I can find an indiscernible sequence where I say x is in the evens and then x is in the multiples of well, I don't know, x is in the odd multiples of 3, x is in the, I don't know, the powers of 7 or whatever. Or I could say x is in the powers of 3, x is in the powers of 5, x is in the powers of 7, x is in the powers of 11. Those are all pairwise disjoint and have the same type, so they start an indiscernible sequence. Okay, so you could do it. But this is the standard example. This one is the ternary order. All right, so now let's try to establish positive properties of this relation. Okay, so the one I want to prove today is extension. And the reason I want to prove this is because I think it explains why you look at forking at all. So here's extension. So suppose A is forking independent with B over A. Then given any C, and remember these are all tuples, not necessarily elements, they could be infinite. There is some A prime, which has the same type as A over AB. So recall this means that it has the same type, such that A prime is independent not just with B, but also with C. Okay, so what's the idea? So the idea of A being independent with B over A is that B doesn't know more about A than capital A knew. So suppose I'm given some new parameters. What I want to do is I want to extend it in such a free way that I don't force any new relations using this parameter. I want to take somehow like a minimally informative extension. so that using C, I can't trap A into a small set too. Does that make sense? I want to take my type and I want to extend it in such a way that I don't impose any new relations that are small. I only want to say things using C that don't commit me to being the small set. I want to avoid the small sets. So how would I do that? The proof is really easy. It's just a compactness argument. So what do you do? Well, we look at the following partial type. So consider the type that says, so I'm going to look, of course, at the type of A over AB, union, the negation of all formulas phi x c. So this is in the language where I can use parameters from A, B, or C, such that phi forks over A. So I just look at the formulas that fork and I negate them all. And if I can prove that that is consistent, then I'm done. You agree? Okay, so towards contradiction, suppose that this is not consistent. Okay, then that means that there's a finite piece of each one that is inconsistent. So in particular, the type of A over AB has to imply a finite disjunction of formulas that fork. So there are phi 0, xc through phi, let's say k minus 1, xc, such that each, that's in each phi I forks over A, and the type of A over AB implies this disjunction I less than k of phi I x c. Okay, but a finite disjunction of formulas that fork is a formula that forks. What does it mean for a formula to fork? It means it implies a finite disjunction of dividing formulas. So if you take a disjunction of two formulas that fork, then it implies a bigger disjunction, namely the disjunction of all the formulas that the first one implies, and the disjunction of the formulas that the second one implies, right? This is also clear from the unions picture, right? Like a formula forks if it's contained in a finite union of dividing sets. So if you take a finite union of sets that are contained in a finite union of dividing sets, then it's of course contained in a finite union of dividing sets. You just take the finite union of the finite union. So, okay, so what did we find? We found that the type of A over AB implies a finite collection of formulas that forks. So A is not independent with B over A, contradicting our assumption. So consistent, let A prime be any realization, then A prime is of course independent, not just with B, but with C, because we've negated all the formulas that fork. Okay, so the way you should think about forking is forking comes from this compactness argument. Suppose you tried to do the same thing with dividing. What would happen? Well, you would negate all the formulas that divide. You would try to run a compactness argument. And if that was inconsistent, then what would happen? The type of A over AB would imply a formula that divides? No, it would imply a finite disjunction of formulas that divides by the same argument. So in order to get extension, in order to be able to take this free extension, you need to look at forking instead of dividing in general, because otherwise the argument just gets stuck. So it seems like a kind of like a stupid trick. You like try to make your argument work, and then you just change the definition to make it work. But what's nice is that in nice examples, dividing and forking are the same. To be contained in a finite union of small sets is the same as being a small set. And so in such cases, forking is easily understood. And that's something we'll get into in the next two class periods. Okay, so that's all I wanted to say today. Are there any questions? No? All right. Well, I'll stop recording then.